Hey class, today here's notes for 3.10 differential equations. And so just to share our goals with us today, our goal is to solve differential equations by using a technique called separation of variables to find two kinds of solutions: the general solution and the particular solution. All right, so let's kind of make sense of this whole idea of differential equations. So let's look at this throwback problem where we're going to do an implicit differentiation. So if we have this following equation, 1/2 y squared minus x squared equals 2, let's find dy dx. And if you remember, how do we find dy dx? Well, we're going to have to take the derivative of the whole equation. And so I'm going to write dx of 1/2 y squared minus x squared equals d dx of 2. And when we do this, we should get, when we take the derivative of 1/2 y squared, we get just y, but chain rule says we have dy dx minus 2x dx, which we know cancels out, and the derivative of a constant is 0. And so I'm left with y dy dx minus 2x equals 0. And if I'm solving for dy dx, it's going to be, let's keep y dy dx here, move 2x to the other side, and then to solve for dy dx, I'm going to divide by y, and so you get dy dx is equal to 2x over y. Yay, fairly simple. Okay, so what differential equations is all about right here? It's all about starting from this point, that dy dx, and we're going to go backwards and solving it to go back to the original problem. That's our goal today. Okay, we're going from a differential equation and going back to the original equation, or what we're going to call a solution. Okay, so let's go backwards and start with dy dx is equal to 2x over y, and then let's do this. Okay, so we know that this, I'll do some terms after. Okay, so we're gonna do a technique called separation of variables, where we're gonna move all the y terms on one side and the x terms on the other. Okay, so bear with me for a sec, but what I'm gonna do is I'm gonna multiply by y to both sides, and what you're gonna see is that it leaves me with y times dy dx equal to just 2x. All right, now notice what happened. Now I have the y and the dy together, and my goal is I want the dx and the 2x to go together. Okay, so what that means is I'm going to need to multiply both sides by dx. That way this dx and this dx cancels out, and we're going to be left with y dy equals 2x dx. Okay, now what's great about that is because our next step, what do you think we're going to do? If you look at the left problem, the throwback problem, we saw that we took the derivative from the original equation to get to this dy dx. So if we're going to go backwards, we are going to need to take the integral of both sides. And what's nice is that all the y and the dy's are together, and the x's and the dx's are together, so we're all set to take this integral. So when we take the integral of y, we get 1/2 y squared plus some constant c, I'll call it c1. And when we take the integral of 2x, we get x squared plus c2. Okay, Now I'm going to clean it up a little bit by subtracting c1 to both sides, which leaves me with 1/2 y squared is equal to x squared. Now what happens when you take a constant subtracted by another constant? We end up with a new constant, so I'm just going to call it c3. Okay. And there you go. So we have a equation that looks pretty similar to where we started over here. Maybe we can rearrange a little bit. So why don't I just subtract the x squared to make it look very similar. So we get 1/2 y squared minus x squared equals c3. Okay. Now, as you can tell, we have a c3 here, but in the original we had 2. Okay. Now that's because this 2 is one particular solution. Okay, this is a particular. While the c constant, which represents all different kinds of numbers, represents a general solution. Okay, so maybe I'll just circle the whole thing. This whole thing is a general solution. Okay. Let's say, for example, let's say we were given a condition. Like, let's say we were given y of 0 equals 2. Let's say we're given this condition. And so that will help me solve for c3. So we got 1/2 of 2 squared minus 0 squared equals c3. And we know 2 squared half turns into 2 minus 0 equals c3. And hey, c3 equals 2. And so we'll know that the equation for this given condition is going to be 1/2 y squared minus x squared equals 2. And this is a particular solution. Okay. All right. Let's move on. So, let's kind of think about what we just did here. We started with this equation, this differential equation, and then what we did next is we started separating the variables, right? So why don't I call that separation of variables. And this was the original differential equation. And there's a separation of variables. The next step we did is we then took the integral to help us find the general solution. And if you're given a condition, you can find the particular solution. Okay. So just to go down here, we have this separation of variables box. And just to kind of talk about it, it's a strategy for solving differential equations where all the y variables, including the dy, is on one side. And all the x variables is on the other side. So just to look up at the top, you notice right here, we have all the y dy's and the x dx's on each side separated. Okay. And one thing to note is that you must have your dy and your dx in the numerator, not the denominator. Okay, that's key. Alright, so why don't we practice just separating the variables for each differential equation, okay? So if we have dy dx equals xy, our goal is, one, to separate the variables, meaning y's and x's together. And the other goal is you gotta have the dx's and the dy's in the numerator, okay? So look at this first one. We have dy dx equals xy. I need to keep dy in my numerator, so that needs to stay. And if that needs to stay, what should I multiply to both sides? I can multiply the dx, because that can go. So if I have dy equals x, y times dx. And now I have the x and the dx are together, which is great. But I need to get rid of the y, so I'm going to divide by y, and then divide by y, or I'll just times it by 1 over y. Okay, so then we have 1 over y dy is equal to x dx. We're all set there. Done. Separated our variables. Okay, so why don't you try the rest? And if you want to do it yourself, you can pause this video. But I'm going to move on to the next ones, and I'm going to go a bit faster. Okay, so once again, the dy needs to stay, so I'm going to multiply by dx. Cancels out, so dy is equal to y squared times dx. Alright, and then I'm going to divide by y squared to give me 1 over y squared dy is equal to dx. And we're actually done. You're probably wondering, well, where is the variable with the dx over there? I guess if you want to think about it, there can be just a 1. And just thinking ahead, remember, after we separate the variables, the whole purpose is so that we can take the integral, and you can see that we're all set there. Doing our next one, we got x e to the negative t times dx dt. So my dx is going to stay in this case. It's in the numerator. So let me kick out the dt right away. So I have x e to the negative t is equal to d1 dt, which we don't need that 1, but that's fine. Now I'm going to rewrite this as x over e to the positive t. I just did a reciprocal because there's a negative exponent, which really helps me because then I can just multiply by e to the t to both sides, and those two will cancel out. My goodness, I just realized we forgot a dx here. So we're left with x dx equals e to the t dt. Set. Next one here, we got dy is going to stay, multiply by dx. I'm going to do something daring here, because I know these two are going to cancel out. I know I need to kick out the y, so I'm going to multiply by y at the same time, so that this y and that y can cancel. So then I'm left with y dy is equal to 1 plus x over x dx, and we're set. Our last part, we have the dy. Our next part, we have dy that's going to stay. So I'm going to multiply everything by dx to kick that out. And I'm going to multiply by 3y squared to get this guy out. So I'm left with 3y squared dy is equal to x squared plus 1 dx. Final problem. Notice that we're in kind of a standard form, so you might want to what happened? Okay. Let's add 3e to the x to both sides, and so we'll get 4y dy dx is equal to 3e to the x, and we can keep the dy, so I'm going to multiply by dx to both sides, and I think that's it. So we have 4y dy is equal to 3e to the x dx, and you're all set there. Excellent. Alright, so in our next video, we're going to actually start doing some examples to solve these differential equations.